The last part of these notes consists of doing some problems based on the equations before. Again, we're sort of analyzing the physics of the capacitor itself, looking at charges, electric fields, etc. So let's calculate the electric field between these capacitor plates. So we have a 3 micro. I see what they're saying. We're saying a 3 microcoulomb capacitor has, and this is the area, this is the plate separation. This is supposed to be a separate charge after so we're going to charge the capacitor with 3 microcoulombs, and this is what I meant to say. So the idea here is that we have 3 microcoulombs here, and then in a later part of the problem, we're going to put like a little 2 microcoulomb charge right there. And of course, let's remember if there's positive 3 microcoulombs on the left plate, that means there's negative 3 microcoulombs on the right plate. Now, to get the electric field is going to be sigma over epsilon naught, and in this case, that means we're going to take the 3 times 10 to the negative 6th. That's the charge. We're going to divide that by the area, which is 2.8. 2 times 10 to the negative 8th meters squared. So that's Q over area. And then we need to take that epsilon naught into account. So that's 8.85 times 10 to the negative 12th. All right. So far, so good. Now let's go ahead and actually evaluate the value of that electric field. So we'll take 3 times 10 to the negative 6th, divide that by 2 times 10 to the negative 8th, and then we'll divide that whole quantity by 8.85 times 10 to the negative 12th. And so we end up getting, I'm getting quite a big number. I'm getting 1.7 times 10 to the 1.7 times 10 to the 13th newtons per coulomb. Quite a big number. I'm going to just double check that one more time. Well, let's see the powers. So 14, actually, let's see, 8 plus 12 plus 20. Yeah, that's a realistic number. Okay. Now, let's calculate the positive work done on the charge of the capacitor as it moves from the left plate to the right plate. So again, the work is going to be Q times E times D from the previous page. So that's going to be 2 times 10 to the negative 6th, because this is the charge that we were talking about, times E, which is going to be 1.7 times 10 to the 13th, times the distance between the plates, which is 0.0005. It's going to be a significant amount of work. Let's just see what that is. That's going to be 2 times 10 to the negative 6th times 1. Let's try that again. 2 times 10 to the negative 6th times 1.7 times 10 to the 13th times 0.0005. That's giving me 17,000 joules. And we want to determine the change in potential energy of the charge. Well, it's losing 17,000 joules of potential energy because it had positive potential energy here. It's losing that over there. So work, remember, work results in a reduction in potential energy because you're taking that work. It's a force acting through a distance, and that gives an object kinetic energy if it's positive work. Positive work means negative change in potential energy. We know that from mechanics. So let's get the speed. So 17,000 joules equals 1/2. Let's try that again. 17,000 equals 1/2 times 2.3 times 10 to the negative 8th times v squared. So when we isolate V, we're going to get a pretty big number here. That'll be 34,000 divided by 2.3 times 10 to the -8th. All right, and then when we square root that out, this is, I think, a classically impossible result. I'm getting that it's about a 1, so I'm getting 1.2 times 10 to the 6th meters per second, which is technically speaking a classically impossible speed, but for the purpose of this problem, we'll leave it here. All right. Now, we want to find, so again, the potential energy of a charged particle is negative QED, whereas the work on it is positive QED. So what we're going to do here is we're going to define a quantity called the potential difference, where you take the electric field times the distance between your capacitor plates. So that's actually how we define voltage, and it turns out that 100% works and defines the voltage that a battery would put across a couple plates. In other words, the voltage that you're used to doing in circuit stuff is exactly the same as the voltage that's going to apply when we do capacitor stuff right here. So the real definition of voltage, the voltage drop, is actually the electric field times the distance with the negative sign in front of it. So when we want to determine the voltage drop across the capacitor in problem 3, we'll actually say that the voltage drop is negative E times the distance across the plates, which is going to be 1.7, sorry, let me try that again, 1.7 times 10 to the 13th times the distance between those plates, which is 0.005 meters. Sorry, 3 zeros and then a 5. So that is going to end up giving us, for our voltage drop, or our potential difference, so that is going to give us 8.5 times 10 to the 9th volts, quite a bit. All right. Now here's an interesting thing. We have the formula for the voltage across the capacitor, and we know that Q equals C times V. So what we're going to do is we're going to actually come up with the formula for the capacitance of a parallel plate capacitor. So in other words, Q equals CV, and we've always accepted this as a number. But what we're going to do is we're actually going to come up with what C is in terms of the physical structure of the capacitor. So it turns out capacitance itself depends on the shape of a capacitor. And what we're going to do is we're going to come up with a formula that describes the capacitance of a specific capacitor, in this case it being the parallel plate one. So Q equals C times V, and we know that V equals E times D. And let's remember that E for a parallel plate capacitor is sigma over epsilon naught. And continuing, we know that sigma is Q over A, with an epsilon naught here, times D. So here's what we end up getting. We end up getting that the charge in the capacitor does equal the capacitance times the voltage drop across it, which is Q times A over epsilon naught times D. So we can cancel Q here. So it turns out the capacitance of a parallel plate capacitor depends on its area and its distance, and the electric constant, the permittivity of free space, epsilon naught A over D. So this is quite a bit to cover, and this is just a preview of the physics of capacitors. We're going to go over this more carefully in class, but I wanted to give you an introduction to how capacitors behave.